Okay, I want to make a video about last week's weekly contest. I was out for it, but I looked at the problems after, and they're really interesting. Not so much Q1. In Python, at least, it's asking you pretty much to just use exactly the split function on a string, which is simple enough. And then this would give you a list of lists of words, and you need to flatten that. And in Python, a pretty smooth list comprehension way to do that is to say x for sublist in res for x in sublist, if x, because they don't want empty strings. And that's kind of how you flatten a 2D list into one dimension. Q2, it starts to heat up a little bit. I'm actually a little surprised that 9,000 people got this. So the idea is we can have a number eat the number to the left of it. So for the 7, we can say, hey, add this to the 9, remove the 7. Then the array goes from 23793 to 23163. And it's not extremely clear how to programmatically go through or greedily go through and reach the optimal number. But if you look at example 1, they're almost a little generous with this example, because you can kind of instantly, your eye is caught with, hey, this 3 is never going to go up, because bordering it to the left is a 9, and numbers can only go up, they can never go down. So this 3 is never going to eat this 9. The 9 can eat the 7, which eats the 3, which eats the 2, and it gets to 21, but the 3 is never going to change. So like if we started there, we can just instantly be like, well, just keep going to the left, drop the 3. As opposed to example 2, which also ends in a 3, but this 3 can eat the other 3, which can then eat the 5. So it'll be 3, turns to 6, turns to 11. And therein kind of lies our algorithm. We just iterate backwards. This is a problem where the tool in your tool belt you want is to iterate backwards. And just kind of greedily go through and be like, the moment we can't eat the thing to the left, it's a larger number. So just take that and keep eating to the left. That's pretty much exactly what I do. The constraints are too tough to actually remove things from the middle of a list, because that's O of n. But you can just use 2 pointers. So I just say, take the last number, the second to last number, keep eating until you can't, and then take that number and keep eating. Okay, now for the really difficult ones. Maximum number of groups with increasing length. So there's a couple of things to notice, and actually this is a similarity that Q3 had with Q4 on this contest, is that oftentimes there's like one really hard there's one really hard cognitive feat you have to make, you have to perform. And here there's multiple things you have to realize. And if 1 in 4 competent coders realize one of those things, then for 2 of them, you're quickly taking this very small fraction of users that are actually going to figure it out. So the first thing to realize that's a little bit sensical or relatively simple, is each group must have a length of strictly greater than the previous group. So if we let's say we separate our elements into a group of size 3 and a group of size 4, there's no reason why you would ever not just have a group of size 2 and a group of size 3, or a group of size 1 and a group of size 2 for that matter. So one immediate thing we can sort of deduce is that our groups will always be of size 1 and then 2 and then 3 and then 4 and then 5 and so on until we can't make any more. And we can see that reflected in the examples they give, the reasoning for their solutions. It's a group of size 1 and then 2 and then 3, because you'd never want to have 1, 3, 4 or anything. You'd kind of be wasting elements superfluously. That's one thing to realize, and I think this problem is best visualized. So if we take example 1 and we say, okay, we know we're going to have a group of size 1, 2, 3, and so on. How do we divvy these up? What's the optimal way to divvy these up? We can look at the constraints and say 10 to the 5th, so it's got to be linear time, or n log n potentially. So what do we do? 1, 2, 5. And apologies in advance. This is I equals 0 means the 0th type, and we have 1 of them. This is the 1 elements, we have 2 of them, and the 2 elements, we have 5 of them. That's sure to trip me up as far as how I talk about them, because that's a little bit of a confusing syntax, that the value is the frequency and the index is the value. But with that out of the way, what do we do? So first thing we could try is just say, hey, take the 1, put it in the subset of group 1, take the 2 and the 5, and so on. But if we did that, we would say, all right, put the 0 there, put a 1 and a 2 here, and then we don't really have anything else, so we just put a 1 and a 2 here. So we can't get away with putting the smallest frequency element to the smallest group. In fact, that's kind of the exact opposite of what we want to do. So if we go the opposite way, we can say, okay, well, hide the 0 off in a large subset. Oops. And then with the 1s, disperse them later on. And then with the 2s, because we have so many of them, then 2 can have its own group and be in every other group, like that. And something you kind of notice that's actually reflected a little bit in their example solutions, this is another little almost hint that they give you in how they order these groups that are unordered, is you see this kind of diagonal pattern. And it's worth kind of pondering that and thinking, is there any way we can just look at a group and say, what goes in this? What goes in this one? What goes in that one? And like, not really. Like, if you dig into that, the problem is pretty much anything is going to be O of n squared or O of n squared log n. So a better way to think about it is, how many groups can I disperse this element into? So here we can say, well, 0 is going to be in one group, 1's going to be in 2 groups, and 2 is going to be in 3 groups. And you sort of see this pattern emerge that's like, if we sort this, then we can see, well, as long as we have one more than the previous, then we can say this goes in 1 group, this goes in 2 groups, this goes in 3, this goes in 4. And even if we had 1, 2, 300, 400, 500, it's still going to be capped at 3, 4, 5. So that kind of checks out. So what if we sort it and then we do this? And then even if you imagine 1, 2, 2, 3, 4, 5, this bottleneck would essentially be, you know, we have strictly more elements than this, so we know we can still reach 5 groups. We would just say, hey, have we seen a 1? Yes. Have we seen a 2? Yes. Have we seen a 3? No. Yes. 4, 5. That kind of makes sense. But then a counterexample you can think of is 2, 2, 2. And here you have this problem where this doesn't obey the rule that we just laid out. Because you could say, okay, put a 2 here, put a 2 and a 1 here, or let's say actually put a 2 and a 0 here, and then put a, fuck, let me think about this. 1, 2 and 1, 2 and 0, and then 1, 2, 0. Yeah. So we can actually reach 3 groups, despite the fact that we don't actually have any element where there's 3 of it. And that makes sense because as we have these diagonals, it doesn't have to be all the same for these. Like here we can use 2 2s and a 1. We just didn't have this 1 in the same group as previous usages of that 1. So that idea is a little bit shot. The idea that we can just check what's the first number that's greater than 2, what's the first number that's greater than 3, and so on in a sorted array. But that's still a useful way to think about it. And if you think about it along these diagonals, we don't care at all what numbers are in this. They can be whatever we want. They could be all 2s. They could be all different elements. If we had, for example, like, oops, 1 1 1 1 1 1, this would be like 1 2 0, 3 4 5, something like that. And we can see if we have all 1s, we can truly just do whatever we want in the entire array. But when it comes to these diagonals that we've drawn, where really now we're not thinking about it as, hey, try to build the next group, but we're saying try to add the next layer. And if we wanted to, let's say we had 1 2 5 10, something like that, we could say 0 2, 2, 2, and then we could just kind of slap on another diagonal and say 3, 3, 3, 3. And then this would be the group of size 1, this would be the group of size 2, this would be the group of size 3, and so on. So thinking about it in terms of these diagonals is still useful, despite the fact that we're not actually constrained by all of these having to be the same. We could have, say we had, instead of a 10, this was like a 2, 2, then we could just say, okay, well, fine, 3, 3, 4, 4, or something like that. And if you think about it, again, not only do these not have to all be the same along these diagonals, if they did, then that would be it. Then we would be done. It would just be check to see the first thing greater than or equal to 1, 2, 3, and so on. So the answer to this would still be 3 groups. But because these don't have to be the same, in fact, they can be any assortment of numbers, it sort of leads us to this next thing that you kind of have to realize. It's a very specific way of thinking about this problem, which is these numbers don't matter at all. These can be whatever we want. So with that in mind, if we have, say, some number I, for example, here we have 6 elements total, and if I remove a little bit of the clutter, and we have 6 elements we want for 3 groups, for example, well, great. Okay, we have all the elements we need, and then the only question is how much variety do we need? And because these 3 elements can be whatever we want, we can draw this recurrence relation where we say, well, we have enough elements to fill 3 groups, and we don't know if the variety is good enough. But to answer that, what we can say is these 3 numbers can be whatever we want, so therefore just take out those 3 numbers and see now, do we still have enough for 3? For these 3, for 2 subgroups. So we can say, okay, take out the largest element, its frequency, and say now we just have 2, 2. Is that good enough? Can we fill 3 spots with that? And the answer is yes, we can. And then we say, well, can we fill 1 spot with 2? Yes. So we see now we have this comparison of prefix sums where we're sort of ignoring a lot of the rules directly, and the way that we're handling them is in the relationship between the answer to one question, whether we can fill this many subgroups, and the next question, whether we can fill the next smallest many subgroups. And we can see if we have something like, let's say we had 1, 1, 100. Hey, cool. Well, we have 102 elements. So yeah, we can fill more than 3 subgroups, which would require 6 elements, and 4 subgroups would require 10, 5 would require 15, 6 would require 21, because you're just adding the next number up in the natural sequence of numbers. But then if we ask the next sub-question, we say, okay, well, what about 1, 1? Is this good enough for 2 subgroups? The answer would be no, because there's not enough elements. And while we did have 100 of this element, we can only use that for up to 3 subgroups before we would have to start reusing them in the same subgroup. So this can only account for 3. And that's why we say, okay, well, what if we removed this element and now we need 3 less, because along this diagonal, we just said use as many as you can for that. Oops, this is supposed to be 3. Then we get this question. So we see really what we're doing now is just comparing prefix sums. So here if we had 1, 1, 100, really what we want to do is take the prefix sum and say 1, 2, 102. And then that allows us to, in linear time, say, okay, compare 102 to 6, compare 2 to 3, compare 1 to 1. And similarly here, if we had 1, 2, 5, we can transfer this. We can have this be a prefix sum and say, now really this is 1, 3, 8. And then we compare this to the prefix sum of all the elements that we need. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So we'd say 1, 3, 6, 10, 15, blah, 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 blah. And then we're capped by really now only two things, just the sheer number of elements that we have. Like, we're never going to be able to fill 4 subgroups with 3 distinct types of elements, so that's out of the question. And then at any given moment, the level of the amount of elements we have to fill this level of variety. So here we could say, hey, 8 is greater than 6, so we're good. 3 is equal to 3, so we're good. And 1 is equal to 1, so we can fill 3 subgroups. And if we go back to our previous example, let's say we took 2, 2, 2, then this becomes 2, 4, 6. And then we compare that to 1, 3, 6, and so on. And then we say, well, can't get that for multiple reasons. But we can have 6. Because at every single step of the prefix sum, the elements that we have are greater than or equal to the elements that we need. So it boils down then to a very simple algorithm that's just takes a lot to deduce. It's a very Excalibur heavy problem. And it's interesting. There's this kind of symmetry to it. But ultimately, this feels more like a code forces problem than a Leetcode problem, because it's a lot of deduction and a lot of math for very simple code. So we just say, okay, sort it, and then every step of the way, take a rolling sum, and this is just an equation for the sum of all numbers from 1 up to n, but it's 1 indexed as opposed to 0 indexed. It's just like n times n plus 1 over 2. Yeah, and then we just say, hey, if we can, create another subgroup. Otherwise, keep iterating forward with our rolling sum. And similar to if we had, say, 1, 2, 5 can give us 3. Similarly, if we had like 1, 1, 2, 5, this is also going to give us 3, even though we don't need to check explicitly, hey, is this greater than or equal to 2? Because we can just say, no, just find the next one that's greater than or equal to 2. We sort of are doing the same thing here, where we're saying, don't just stop the moment you find any bottleneck. Like, wait until you find something that suffices and then add 1 to j. J being the number of subgroups we're looking for or able to achieve. And then in the end, that's just what we return. So it's an interesting problem. I think the real difficulty is in keeping straight in your head this diagonal relationship and the features that this question has of what you can put in here, as opposed to this question of what you can put in here. And honestly, I thought Q3 was harder than Q4. Q4 was more graphy, and those are always a little more fun and satisfying in a way. But this one's, the numbers say it's even harder, because I think there's even more kind of hoops you have to jump through, cognitively speaking. So one of the first things to recognize, and it is often for these harder problems something that arises, is that bit masking is on the radar. We see, okay, n is up to 10 to the 5th. We're looking to evaluate in some way all pairs of nodes, the paths between all pairs of nodes. But O of n squared is too large. And if we were evaluating the path between every node, that actually would be O of n cubed, because we could have some linked list of a tree where a path's evaluation is O of n itself, and then you're doing that O of n squared times. So that's totally off the table. We can't do that. We have to find multiple ways to optimize. And one thing that we can kind of think about as our eyes kind of look over the constraints is not actually in the constraints. It's that the values for these edges can only ever be letters in the English alphabet. This isn't like the Chinese alphabet or something where there's thousands and thousands of letters. There's exactly 26. And something that my mind always does is it says, hey, what's 2 to the power of this small thing? Is this usable? Like 2 to the power of 10 is around 1,000, which means, you know, we're going up by 3 orders of magnitude base 10 if we decide to do this operation. So sometimes you can get away with like O of n times 2 to the power of m or something like that. But here it's 2 to the power of 26. And 2 to the power of 26 is a little too large. It's 67 million. So somewhere around 10 to the 7.5, a little more than that, which is too large. That's decidedly not going to work. But it's something to think about, because we can still represent a bit mask of some amount of characters, some set of characters with an integer. It fits within the integer limits because it's less than 31, less than or equal to 31. So with that in mind, we look at the problem a little more, and then that sort of begs this question. A bit mask is essentially a set. You just have to have at most 31 of the element, and then you have a set that's hashable. So how can we use that? And the thing about a set and a bit mask, it's binary, unless you're doing some base K bit mask, which there are problems like that, but you know, this hopefully isn't one of them. If we have just a regular ones and zeros bit mask, we're sort of saying, okay, there's either a 1 you can ascribe to a given character or a 0 you can ascribe to a given character. And that actually matches up relatively well with this notion of a palindrome, and specifically something being rearrangeable into a palindrome. Because we can see like all the palindromes here, well, every single edge is itself a palindrome because that's just one character. But beyond those, CAC, ACA, ACAC, all of those can be rearranged into palindromes. And something that is true about palindromes is that at most you have one odd element. So CAC, A is odd. You could have 2 C's, you could have no C's, which is another palindrome in this thing. You could have 100 C's, you could have 1,000,000 C's, but at most you can have one character where there's an odd number of it. If you tried BCAC, there's nowhere to put the B. You would need 2 B's or 4 or something. And similarly, ACAC, there you have no odd numbers. So you need to have at most 1. If this B was connected to the 3, and you could have BACAC, that would also be valid. And then I guess the output would be 9. So with that in mind, we realize, hey, there's this parity that we need to look for, which is some path that has at most 1 odd frequency of characters. And then that's really useful for bit masking, because then we can say, hey, we don't really care about the amount of a given character. We just care whether it's odd or not. And that's really easy to do. If you have a mask and you say, say our mask is like 01101 or something, and then we encounter an A that we've encoded to be like 1 bit shifted over to the 0th times because it's the 0th character, then we can say, hey, just take 01101 and XOR it with that. XOR it with 1 to the 0. So then we get 01100. And we could do the same thing with B, which would be 01101 if this was 1 bit shifted over to the 1. And now we have this really useful way to represent the parity. And also, then, if a mask represents a path, we have this useful heuristic that immediately pops up, which is, okay, if all the 1s are all of the odd numbers, any mask that has 1 set bit or less is valid. So if we ever have a mask that's just all 0s, that's always valid. That just means like there's an even number of every character. If we had like this, or let's say this, let's get rid of this stuff. It's not relevant anymore. If we had this, and we've, again, encoded 1 means A, 2 means B, 4 means C, 8 means D, and so on, this would mean, hey, we have all an even number of other characters. Maybe that's 0, maybe that's a million, who cares? And we have exactly an odd A and nothing else. So this is also valid. So now we have this way to say, hey, any bitmask where there's an odd number of one thing or nothing, that's a valid path. So already that's very useful information. And that's kind of building upon itself, but there's still this problem of how you actually evaluate a path in O of n time, how you evaluate all paths. And this is where the second thing comes in that's really tricky, which is that if you have, say you have, like a path like this or a tree like this, and you say, okay, this is A, this is A, this is C, this is B, something like that. Okay, we have all the single edge palindromes. Those ones are kind of a gimme. And then we have like this palindrome, AA. And how do we find this? How do we evaluate this along with every other path between two nodes in linear time? Which feels like an impossible task because you're evaluating n squared objects in O of n time. And this is where something really tricky comes up, where this sort of tree pathing and a property about things that have the potential to be palindromes comes up, which is, what if we drew, instead of AA was our palindrome, what if we drew ACB CA? So we just went through the root every time. It's quite phallic, but then we would have A, C, B, and then B, C, A. So we can see, hey, that's palindromic. And that's something that doesn't really come up in the examples, because the examples don't have that quality. If 1 to 4 was A, then it might beg that question more, but this is something that you kind of have to like come upon with yourself in Excalidraw. Yeah. And what this leads to is this idea that we can reliably draw superfluous paths that are longer than they need to be between two nodes, that if those are palindromic, then the path between two nodes are palindromic. And we can always draw this path through the root, because we can always say, well, you know what, if we're going superfluously through the root, say we had, something down here, something like that, and then we had some other thing here. Say, again, we're looking for these two nodes. Hey, is this relationship palindromic between these two nodes? Then what we do is we say, hey, just go up, and then we have A, C, B, B, C, A. That's going to be in the middle, and then that's going to be sandwiched between these characters. And then really the evaluation is, are these the same? And it's superfluous information, this extraneous path that we're taking, which seems like, why would you ever want to do that? But then there's a really useful thing we can do, which is we can standardize our paths, and we can say, okay, you know what? From now on, all nodes, all of their paths are from the root to that node. So this one, any path is going to go through the root. This one, any path is going to go through the root. All of these are subservient to the root. And if there was, some other whole subtree over here, then great, then there's a reason for that. But if there's no reason for that, then still it's a way to just standardize the paths. And we know that that's not going to change the relationship between these paths and whether or not they're palindromic. So that's the second thing to realize here that's quite tricky, is that anytime you're taking a superfluous path, I think this is the most succinct way to put it, anytime you're taking a superfluous path, say instead of from here to here, here up to here and back to here, all you're doing is adding in exactly 2 of this character. And you're even adding it in the middle. If this didn't have to be rearranged, this would still be the case. But or if you couldn't rearrange the characters, it would still retain the palindromic quality. But the fact is, you're adding 2 A's. If you go up to here and back, you're adding 2 C's. You're always adding 2 of a character. So that's not actually changing whether or not something is palindromic, because you're not changing whether anything in the bitmask is odd or not. Okay, so there's these multiple tools that we have that are sort of coming together. And I think the fact that you need to come upon all of these kind of and then find a way to use them is quite the feat of detective work. And then the question is, okay, we have all these paths, and it sort of makes sense. Say we take this. Oops. We take this and we say, okay, 0 to 3, that's CA. 0 to 5, that's AC. Or whatever, both of them are the same bitmask. Then we can say, hey, if these are equal, then when you combine both of them, you will have a bitmask of 0. AKA, if these contain the same characters, then you can have a palindrome of even length. You can have a palindrome where there's an even number of every character. But say you had like CA, say you had, let's just draw a little fan fiction addition to this graph. Say you had a B right here. Oops. Sort of like before. Here, you could also say, hey, well, CAB and CA also works, because when you combine both of those, you don't get a bitmask of 0 because they're not the same, but you do get a bitmask of exactly a bunch of zeros, 1, 0, because there's an odd number of B's and everything else is even. And then you can say, hey, this is what we're looking for. So this is where we actually can use bitmasking to begin to optimize significantly on the time complexity. So what we can do is we can just say, hey, for this path, say, check this other path, and then say, if this other path gives us a bitmask that has exactly one set bit, 1, 1, and 25 zeros, then this is a working path, and we can add 1 to our result. So then what we do is we say, just check through, just iterate through I equals 0 to I equals 25, and then say, hey, is 1 bit shifted to I, 1 bit shifted I times? Is this a 1? If so, this needs to be the only one that we see. If it's a 0, then we can keep going. So this gives us a way to now reconcile two paths, which is useful. And then the question becomes, how do we reconcile all paths with each other path from the root to a given node? Because ultimately that's what we're looking for, is a path from the root to a given node, if you combine it with a path from a root to another node, does that have at most one set bit? And that question actually is like not the hardest thing ever to answer. If we had a large array, let's take a different problem for a second. This problem is already very convoluted and confusing, so I'm not especially worried about adding to that. Say we had like 1, -1, 5, -5, 6, 7, 0, something like that. And what we're looking for is all subarrays with sum of 0. This is a problem that shows up quite a bit. And what you can do is you can just take the prefix sum of this and say, okay, 0, 1, 0, 5, 0, 6, 13, 13, 6, 3, 0. And what you notice is, hey, everything with a 0, that's a subarray up to this point that adds up to 0. So the whole thing adds up to 0, or this adds up to 0, 0, 1, -1, but also anything that's equal. For example, 13, 13. That's this 7 and 0. You're saying, well, hey, this is a subarray of sum 0. Or 7, 0, -7 is like this 6 is equivalent to this previous 6. And this is a way to evaluate. There's O of n squared ranges with sums, but you can evaluate it in linear time by just keeping a count. Like, how many zeros have we seen? Have we already seen a 0? So for example, here we're like, hey, we've actually seen a 0 already. So 0, 1, -1 works. Or here, we're like, we've seen a bunch of zeros already. So what would it be? This works. This works. One of these works. This works, and then also this works as subarrays with a sum of 0. And we can transfer this sort of strategy of iterating through and just keeping a counter of the amount of times we've seen a given thing. We can extrapolate that into this problem as well. So we can say, hey, how many times have we seen AC? So when we first outline this AC, we say, well, we've seen it 0 times, so keep going. And then when we outline this AC, we're like, hey, we've seen a single AC. So now we have a working palindrome, a working thing with an equivalent number of characters. And then with a situation like this, where we want to have BACAC, here we'd say, okay, we have this random bit mask representing CAB, which I guess would be 7, is what the bit mask would be. And then here we would say, hey, this bit mask is 3. And then we would say, okay, XOR them together. Now we have 4, because 7 XORed with 3 is 4. And then we would go through and we would say, or I'm sorry, this wouldn't be 4, or 3. This would be 5. 7 XORed with 5 would be 4. And then we would say, hey, does 4, do we have that? Or I'm sorry, does this have a set, only one set bit? And the answer is yes, which would represent, hey, if we combine BACAC, we have a palindrome with at most one odd number of any given character. So with that in mind, I think it's worth starting to look at the code. First thing we do, we just build the adjacency list. And then we have this kind of scene dictionary, which, similar to this subarray sums question, we're keeping track of all of the bit masks that we've seen previously. And then I just run a simple DFS. The idea that you need to use DP or anything like that, I think, is not relevant to this problem. Even though for these complicated ones, I think a lot of people's minds immediately go there. But we are keeping track of two things. We're keeping track of what's the current node we're looking at, and what's the current mask representing the current path from the root to this node. So the first thing we do is we say, hey, if we're at node 0, just ignore it. That's not, node 0 doesn't matter. Node 0 is this in scene. When we say scene at 0 equals 1, what we're saying is we've already seen a bit mask of 0, aka a bit mask of 0 is a palindrome itself. So for example, if we had CAB AC, something like that, this is itself a palindrome, CABAC. And that's just the path between this and the root. So really the root itself is like a 0, a bit mask of 0 that we get for free. So that's why we say scene at 0 equals 1. That's also why we say if u here, u being, that's a confusing way to put it, u being the current node's index, because u equals 0 is always the root, and the root doesn't have any edge leading to it. The root leads to other nodes. So then we say, okay, well, if we're not looking at the root, add the current edge of this node leading to this node into the bit mask, and then check, hey, how many viable other bit masks have we seen that correspond to this bit mask? And the way that we check that is just, hey, try and take every single character as the odd one, as the center of this bit mask, and see, hey, if we had one extra Z, do we have another bit mask that's equivalent to this, where what we would get is 1 at the Z's place and then a bunch of other zeros. If we had an extra A, if we had an extra B, for every single character, check, which means for any bit mask, any given bit mask, there's going to be exactly 27 other bit masks that can relate to this, 27 other calls to scene where we're saying, hey, how many of this have we seen? Most of the time that'll just be 0. It's going to be, if all 26 characters, if we try and elect all 26 characters to be, each of the 26 characters to be the center of the palindrome. And then also if we say, what if there's no center to the palindrome, which just means, have we seen this exact bit mask before? For example, when we see AC here, we've already seen CA. So we've already seen a 5-bit mask. And then we're like, okay, cool. Well, now we have another 5-bit mask that can just go with that one. And then we add one to the scene at this mask and call DFS. And I think the final question really here is, can we get away with just a straight up DFS like this? And if you think about it, it doesn't really matter almost the order that you go in. Once we have this idea that we can just draw a path from the root to any given node, we can do whatever we want. We could evaluate this AC first. We could evaluate this CA first. All that matters is just like if you do it to every element once. Similarly with the subarrays question, you can evaluate this however you want. All you're looking for is like, for this 13, how many other 13s are there? For this 0, how many other 0s are there? And it's true that like for this 0, you're adding 2, but then for this 0, you're adding 3. But if you think about it, because that's a function of all the zeros you've already seen, the fact that there's 4 zeros necessitates that you'll always get the same number, 1 plus 2 plus 3. Kind of reminds me of Q3. But here, similarly, the order of how we parse these nodes doesn't really matter. So we can just do a straight up, like basic depth first search recursively. And then we would go through and we would say, hey, we've seen a C, we've seen an AC. Let's ignore these nodes. We've seen a CB, we've seen an A, we've seen an AC. Hey, we've already seen that. So now we actually do have an extra palindrome. And actually, when we see this A as well, we would say, hey, we've seen an AC, which itself, when we compare that bit mask with this bit mask, when we XOR them, we get a bit mask with exactly one set bit at the 4's place, which represents, hey, when we match these paths from the root to 3 and the root to 2, these node IDs, we get a bit mask with exactly one set bit. Yeah. So this one's a trek. Recognizing that bit masks are kind of a necessity here. I think that's the first thing, and sadly that's the easiest thing. Recognizing then that a path from a given node to a given other node can always go through the root, and that won't change the quality of whether it can be rearranged into a palindrome. I think that's the really big hurdle here to recognize. And then for me, kind of the third interesting thing of note is that it doesn't really matter how you parse the nodes. I think that's a second, another thing that's important, because I could see someone getting stuck on like how you parse these and how you keep track of what you've already seen and what's in the scene dictionary. But yeah, it's an interesting one. I think this one, Q4, requires a lot more kind of wily wit and creativity, whereas Q3, if I'm being honest, I think requires the idea that you use these prefix sums requires an extreme acuity and unflinching understanding of recurrence relations. And at the end of the day, I think for both of these questions, it's just a lot of confidence in your own capacity to problem solve. I think for a lot of people, that's their largest impediment. Anyway, hit like if this helped.